Hey guys, welcome back to Genius Learning. Okay, so continuing on the series, we have a wedge or ramp with a mass on it, okay, and then the mass is being pulled by a rope. Someone is pulling the rope or someone is towing something. It's being pulled up in this direction by a force of 50 newtons, okay, and given a 20-degree angle. I like to write on the side sometimes. You may find it, helpful or desirable to know all the things that are given to you on one side. The coefficient of friction between the ramp and the box is 0.36. And just fun fact, this number is always under 1. So mu is always going to be under 1, just in case you calculate for mu and you get something over 1, it's definitely wrong. So you want a decimal. So this part right here, so this is giving friction of 0.36, and we have a mass 3.4 kilograms, the force 50 newtons, and the angle. Okay, so now we need to find the acceleration that's going on as a result of this force pulling upward. Let's establish a couple of things before we start, okay? The first thing is crucial is a coordinate system, okay? So is up going positive, is up going negative? How do you feel about that is really what it comes down to. So if you like complicated things, you might say negative, but I'm gonna put positive X in that direction, and here we're gonna put negative X, right? Going up in this direction is positive Y, and going down is negative Y. Okay, so I chose Y in this direction because it's perpendicular to the box. Okay, and that's going to be important. So we got our coordinate system, that's first, and we want to find acceleration. So let's just write that. Acceleration. That's what we're interested in finding. Okay. Now let's do the components. Okay, so I have another video showing this part in more detail. I'm gonna try to be detailed, but I'm trying to be a little quicker for these. And I may be talking crap, because I'll probably do it anyway, but this is important. We're gonna break this box into different components. So basically we're going to show the free body diagram of this situation here. I think I'm just going to do it right on the drawing, right? But usually I'll put a box here and do it, but I think it'll be more beneficial to show you here. The first thing you want to do is always I put mass times gravity, because every object is subject to mass times gravity, or is being pushed down, right, by gravity, and it has its mass multiplied with it. So I'm gonna draw a straight line right from the center going all the way down. So if this is Earth, right, flat, or what, not flat, but this is ground, the ground is flat, and you want the line to be straight even if you're on a wedge. Okay, so this line is going to represent, let's extend it a little more. This line is going to represent mg, right? M for the mass of the box, gravity, whatever. This one is the most important. From there, now we can make moves. So let's choose, okay, orange. Now the second thing I like to do, and this, I feel like it's just, if you want to go by logic, I think this will be a better route. You do your mg, then I do the normal force to the box. Remember that the normal force is always perpendicular, right? It's perpendicular to the surface. So this, crap, I got black on it. All right, so this is the normal, right? It's gonna be an arrow going up. This is the normal force. This force right here going up is the ramp pushing up on the box, right? Because that's why the box does not fall through the ramp. There's a force being exerted from the ramp going upward, and that's the normal force. And now let's display the box pushing down on the ramp. Okay, so we're gonna extend the line going backwards from the normal. I'll say right around there, okay? And we're gonna stop there and look at what I'm about to do. Okay, we have this 90 degrees box in this corner, and so we're using this angle. And in here, right, you can kind of see that this is 90 degrees. Okay, and so we're gonna use this triangle in here. It's usually not explained to people, but this is exactly how we're gonna get the components for what we need. All right, this is the longer side, this is the shorter side, and so the same here, this is the shorter side that doesn't have the angle in it. This long side, which is this side, has the angle in it. So let's do it in red, and it's in there. So if you're confused by that little step, go watch the other video and I have it in great more detail. So we have this triangle, right? And we got the angle in here that's the same as this one. Should have wrote 20. Okay, I'll write 20 under here, but just know that I messed up. I should have just put 20 just to not, you know, this angle is the same one as this one. Okay, now let's do things with that angle. Okay, so we did the normal first, then we extended it backwards to describe the box on the ramp. We're gonna do this right here is gonna be hypotenuse. So we're gonna have adjacent over hypotenuse, right? And we're gonna have mg cosine of theta. Okay, so this whole line right here is mg, right? And so we're gonna use that to describe this side here. So let's maybe write in blue this part. Okay. All right, now we have the normal, we have mg cosine, which is the box pushing back down. Now let's break this up one more time into a component that'll describe this motion, because this box is falling. Let's say this box fell on this ramp, right? mg, the reason it's falling down is because of gravity, right? But the ramp is at an incline, and so the box wants to do this and start sliding down. That is the box sliding in that direction as a result of gravity. So the reason it's doing that is because of gravity, and we want a vector here to describe that. We already have a vector here to describe it going into the ramp. We need one like that. Okay, so let's break this. Now we're done with that triangle. Let's break this up into another triangle now. I'm gonna be parallel to this line, so like that. I'm gonna do right? With that, I'm gonna do this and this, which is 45, 45, which makes a whole 90. So now you see that we got another 90. I'm gonna highlight it with a different color because that one is a little harder to see. Whoa, sorry about that. Oh, that sucked. Okay. All right, so, wow. Okay, so we have this triangle in here, right, that we did first, and now we just extended a line this way, right, a vector. So we should have a little arrow, and we found this 90 degree box right here. So with that, I'm gonna highlight the whole triangle now that we're gonna use. So so you can better see. Okay, so with this 90 degree now, we're gonna use this big triangle here, and the angle is still gonna be the same. All right, so now let's do opposite. We got opposite all the way over here, over hypotenuse. Okay, so we got mg sine theta. And so I'm gonna take this vector and put it up here, because that's the reason we did this little triangle in the first place, to describe the motion that this is falling in this direction. Just like the motion that this thing was falling on me. Sorry about that. Let me just adjust it a little bit. Okay. Yikes. Okay, sorry about that. So now let's put this up here. We're gonna let's put it in orange, the same color we've been doing. So we got, this is gonna be mg sine theta, okay? And remember that the theta is 20 degrees. So all the thetas you see in here are just 20. Okay, so we got that out of the way. We got the gravitational force out of the way. We know this force was already given. We did our normal, and we did the equal and opposite. And now we need one more thing. We're given the coefficient of friction, so we know there's friction. And so like I've said before, and I can't stress enough, the box is moving in this direction, friction opposes the motion. So friction is in the opposite direction. All right, friction always wants to slow you down. And so it makes sense that friction is gonna be in the opposite direction of the motion. So this thing is moving that way. We're gonna put another line like this, an arrow, for friction, denoted by F and K, subscript K, which is kinetic friction. All right, the length of these don't matter. So just to show that in this direction, there's a force happening. In this direction, there's another force happening. There's a force happening up here. There's a force happening down here and to the right. We described all the forces that are on that box. Okay, so just to be clear, we got 1, 2, 3, 4, 5. All right, now let's do stuff with it. Okay, so now that we have our forces, let's do the sum of forces. Okay, the sum of forces. And we're gonna sum up all the forces in the x direction first, okay? So what do we have? We have this is our x direction, so we have this one and these two back here. So this one is positive, so I'm gonna write 50. I'm gonna leave out the newtons, so I'm not gonna do units. So that's positive, and negative mg sine theta, and negative friction. Okay, all of that equals ma. Okay, so this thing is moving. So this entire thing is F, your force acting on the box, equal to ma. That was the formula that we just used right now. The sum of forces is equal to ma. And so this one is general because it has no subscript, but here we're using x. Then the next we're gonna use y. Like why this thing fell as I was doing the video. Ooh, salty. All right, we know the formula for friction. All right, so let's not play games and let's write that down. We got, let's see. We should write it, let's write it here. So we got friction kinetic is equal to mu times normal, okay? And we don't know what normal is yet, but let's move on to the next force in the y and see if we can find the normal force. So the sum of forces in the y now. Okay, so the sum of forces, x and y, are being described. We did the x, now we're gonna do the y. We have normal going up and mg cosine going down. So we got normal is positive and mg cosine of theta is negative because it's going down, is equal to 0. Why 0? Because this box here is not moving in this direction. So as it slides here, like the force is pulling it, so it's going like that, but it's not going like this, like up and down and bouncing on the ramp. It's perfectly leveled on the ramp, and because of that, this force and this force are balanced out, or they're equal to 0, however you want to look at it. So if this gravitational force was greater than this one, it would crush the ramp. Or if this gravitational force was less than the normal force of the ramp pushing up, then it would float up as it moved to the right. But that's not the case, right? So this is perfectly on the ramp, and because of that, these two are equal to each other. Or both of these added up are equal to 0. I wrote both of them added up are equal to 0, and so when I move this to the other side, you're gonna see that they're both equal to each other. So you can see it both ways, okay? Now we have an expression for normal. So let's rewrite this formula and let's see how it's really looking. So we got force of friction is equal to mu, and the normal force is all of this. So I'm gonna write mg cosine theta. Okay, don't get this one confused. This is mu k, kinetic. All right, let's make sure I got room. And I don't, but let me see how much I have left. I could write it on this paper. Okay, so let's see. We have the sum of forces in the x and the sum of forces in the y. Okay, let me just adjust this so that way I don't have to do anything weird over there. Sorry about this. Wait 1 second. This. All right, I think that's enough. Okay, so let's continue. We solved the sum of forces in the x, the sum of forces in the y. The sum of forces in the y gave us normal is equal to something, right? Because we know the formula for friction, we're able to replace the normal, and now we have this good looking formula up there. Okay, so this is what we need to use and replace in here. Okay, so we're gonna do that. We're gonna write this entire thing again, but now we're gonna replace friction, the kinetic friction, with this value here. Okay, so let me choose another color. So I'm gonna do 50. This is for the f of x, the sum of forces in the f of x. Okay, we got 50. We got minus mg sine theta. And we got minus all of this. So we got mu k. We got mg cosine theta. And it all equals ma. Okay, so now we're in a better position to solve for acceleration, right? Because this was the goal of the whole problem. So we only have one term for acceleration, and I think we have everything. We have the mass, gravity, the angle, we have kinetic, the mu. So we had everything. Let's divide this m to the other side, and so we're gonna have 50 divided by m, right? I'm gonna divide this m by all three terms, okay? So another algebra move, I think I might just do this in one step. because of the lack of room. So if I divide out m, I'm going to divide it here, I'm going to divide it here, and I'm going to divide it here, which I already did here. This is going to cancel with that one, and this one's going to cancel. Obviously, this one's going to cancel. So there's no more m's except for under the 50, because the 50 didn't have an m to cancel it out. So now, moving forward, we got minus gravity, sine theta. That's what's left because the m was canceled. Let me cancel it out a little darker now. Okay. Minus mu k g cosine theta equal to a. All right, and let me see if I got space. Okay, I'm gonna push it one more line to go. So last line, let's do a different color to make sure we can see it. And we're just gonna plug everything in. So I'm gonna write the A on this side. I'm not gonna change it. I'm not gonna even touch it. Don't worry about it. Let's just put the values in here, okay? So we're gonna put 50 divided by m mass, which is 3.4. So 3.4 minus 9.8 for gravity, sine of 20 degrees, minus mu k, which was given, 0.36. All right, again, we got gravity, and we got cosine of 20 degrees. All of that is going to equal to acceleration. So make sure we got it all. Ooh, it's looking a little up. We missed the m. Okay. So under here is just 3.4. And everything is going to equal. Let's see if I calculate it out. Where is the calculation? I'm a mess for this problem. Okay, so we're gonna get a total of, I'm gonna write it over here again, 8.03 meters per second squared. That's for acceleration. Okay, then you can put vector over it. So this is the acceleration we're gonna get when a force is applied in that direction. We have the mass, a certain angle, and a certain mu, which is the friction. And this is how much we're gonna be accelerating in that direction, okay? Again, sorry for that inconvenience, guys. Hopefully it will be more stable in the next videos. Thank you for watching.